Right, okay, good morning. So today we're going to be looking at this interesting system that we've got here, which I call the trapezoidal pendulum, which is a system made of two pendula connected together by an inextensible string, and they can just oscillate backwards and forwards like that. The thing we're going to be interested in is measuring the time period of this pendulum and thinking about how that time period varies depending on various distances. So for example, the distance between the points of attachment, the distance in terms of the length of the pendulum, and the distance here in terms of the string that connects the two pendula together. Alright, to put this experiment into context, let's consider the case where we've got a single pendulum. So that's one bob, one piece of string, and we can set it oscillating backwards and forwards like so, and we can measure the time period of a single oscillation. And what we'll find is that the time period is closely related to the length of the piece of string. The system we've just looked at is the classical simple pendulum, and the theory of this is well known. So we've got a pendulum of length L, and m is the mass of the bob, and the system will oscillate in small angles about vertical. And the time period of those oscillations is given by this expression here, 2 pi root L over g, where g is the acceleration due to gravity, which is about 9.81 meters per second squared. To set up the trapezoidal pendulum, all we need to do is make an identical pendulum to the one we had before. So that means using the same mass for the bob, and it means making the length of the pendulum the same. And then we join the masses together with a piece of string. So I'll just do that. Okay, once they're joined together, we just hang up the second pendulum. And as you can see, we've made sure that the separation distance is longer than the distance between the separation between the two bobs, so we can get the whole system oscillating backwards and forwards like so. The effect of this second pendulum is to introduce some new parameters. So let's see what those are. If I draw in our second pendulum, so it's got the same length as our original pendulum, and the mass is the same, and we've tied them together with a piece of string. So we now have some new length scales in our system. We've got the length scale representing the separation between the two masses, which I can call B, and we've got the length scale of the separation of the suspension points, which I can call A. And this whole thing then makes a trapezium shape. We can also define the height of this trapezium to be a length h. Now once we've got all these different parameters together, we find the time period is different to what we had before in the simple pendulum case. In fact, what it does is it introduces a correction factor. So given our time period for the simple pendulum, if we've got all this new trapezoidal pendulum, then the time period changes by this correction factor, which I'm just going to pin up. This whole term in square brackets must multiply our original time period. Okay, so what we can do then is we can think about this equation for the time period of our trapezoidal pendulum, and we can think about how we vary all these parameters. So that's the distance b, and the distance a, and the distance l. And you can decide how you want to do that yourselves, but it's worth noting a couple of important points. The first is, if we set this distance A, the separation between the suspension points, to be about the same as the separation of the masses, then the pendulum oscillates with about the same time period as it would if it were just a simple pendulum. Okay? If instead I make the separation between the suspension points much bigger than the separation of the masses, then what you'd find is that the time period is significantly shorter in the case of the simple pendulum. A really beautiful property of this system can be understood as follows. Let's suppose that I construct two different trapezoidal pendulums. Let's say I label the parameters of the first one A1, L1 and B1, and I label the parameters of the second one A2, L2, B2. Let's suppose also that the time period of the first one is tau 1 and that the time period of the second one is tau 2. What happens is if I make these two pendula, even if they're of different sizes, if I make them have the same proportions, and by that I mean that the ratios A1 over A2 is the same as B1 over B2, it's the same as L1 over L2, then it turns out that the ratio of the time periods are related as follows. T1 squared over tau 2 squared, sorry, tau 1 squared over tau 2 squared is the same as the ratio of the parameters. Okay, that's it. That's my trapezoidal pendulum. I think it's a really beautiful system and it's definitely worth experimenting on in some detail. So go away and enjoy and let me know how you get on. Cheerio. I think we've probably got enough footage, you think? You don't walk off from that. It's done well, hasn't it? It's got all the way across. You're letting him walk out the frame. His back wheel fell off.